Hello everyone, and welcome back to this series on multivariable calculus, and today we're going to be continuing our journey through the realm of vector calculus, that is the realm where vectors in linear algebra combine with things from the calculus world. Right? So last time what we discussed was entities known as vector functions. Vector functions, which took objects U and mapped the set R, the set of real numbers, onto R2 or higher dimensional spaces, right? So here this is going to represent a number, and this is going to represent a two-dimensional vector. In particular, as an example, we can consider the function u of t is equal to cosine of t sine of t. And if we range t from, say, 0 to 2 pi or minus infinity to infinity, what you're going to have is the graph of that associated vector function. And what it's going to do is it's going to trace the unit circle in the counterclockwise direction. In particular, what you're going to have is a bunch of vectors that are going to follow this particular path in that particular direction. Right? And that is what we refer to as a vector function. Now what we're going to do is introduce a new idea known as a vector field, which is going to be an object, capital F, which is going to map R2 to R2. Here, what we're going to be mapping a point, which is technically a two-dimensional number, to a two-dimensional vector. So every point gets a vector, just like before, every number gets a vector. All right, so let's actually note that, because I think that's a useful way to think about it. So each point in R2 gets a two-dimensional vector associated to it. So let's begin by looking at a particular vector field and seeing if we can look at it or generate the vector field associated to this particular expression. Let's define f of xy to be equal to the vector x minus y. So again, what are we working with here? So I give you two numbers, x and y, and you give me a two-dimensional vector, x minus y. So just like we do every time we learn new graphing methods, let's start off with a table of values. So what we're going to be given is a point x comma y, and then we're going to be given an associated vector, f of x, y. So let's choose a few numbers. Let's go through them one by one, just a few. So let's consider, for example, the origin 0, 0, 1, 0, 0, 1, negative 1, 0. Let's do 0, minus 1. And then let's do some inner cardinal points, 1, 1, 1, minus 1. Let's do minus 1, 1, and minus 1, minus 1. Right, so those focuses on, at least hopefully we can get a sense of what the big picture is, and then extrapolate from there on continuously. So once we plug in these numbers, so when we plug in 0, 0, we're obviously going to get the vector 0, 0. When we plug in 1, 0, we're going to get the vector 1, 0. When we plug in 0, 1, we're going to get the vector 0, minus 1. And then when we plug in minus 1, 0, we're going to get minus 1, 0. And then when we plug in 0, minus 1, you're going to get 0, 1. And we can continue this all the way down. 1, minus 1, 1, positive 1, minus 1, minus 1, and minus 1, 1. So once we have a sense of the vectors at a staggered set of points, and obviously computers, software can help you make this more streamlined, then we can go to our Cartesian graph, and at every single point we're going to plot a vector. So at 0, 0, we have the 0, 0 vector, which doesn't point anywhere. At 0, 1, we have the vector 0, minus 1, which is going to point downwards. At 0, minus 1, that's going to be the vector 0, 1, which is going to point upwards. And then if you go to the point negative 1, 0, that's going to be the vector negative 1, 0, which is going to point leftwards. And then if we pick the point 1, 0, that's going to be the vector 1, 0, which is going to point rightwards. And then if I pick, for example, these inner cardinal points, then what we're going to see is we're going to have a vector pointing in that direction, that direction, that direction, and that direction. Right? So when you actually streamline or create vector flows of this particular expression, we clearly see that we have streamlines going down the top side of the axis and going up the bottom side of the axis. And on the left, things are moving west, and then these are going to move east. And what we have here in quadrant 1 is flow lines that are sort of going in that particular direction, that particular direction, this particular direction, and this particular direction. Now, if you've ever taken differential equations and studied systems of diffeeqs, you should recognize this picture as a saddle surface. Right? So this looks like a saddle surface, or at least the level curves of a saddle surface. Or in the realm of dynamical systems, that would be a saddle node. Right? So another thing that we could possibly even say is that fxy, which again is equal to x minus y, is actually equal to the gradient of a particular function, in particular 1/2 x squared minus 1/2 y squared. So if you take the derivative with respect to x partially and then the derivative with respect to y partially and put them in a vector, you're actually going to get the vector x, y. And if we look at the level surfaces of this particular graph, so the level surfaces or the level curves of this function here, let's call that little function f, then what you actually get is that particular saddle surface, right? So it's very similar. Not necessarily equal to each other because they represent different things, but they are similar nonetheless. And also keep in mind this curve does have a saddle point at the origin 0, 0. So there are definitely lots of similarities between the level curves of this saddle surface and the representation or the vector field that is generated from this vector x minus y. Right? So every time you can actually find a function such as this, 1/2 x squared minus 1/2 y squared, that is equal to this vector field, we usually refer to this as a gradient vector field. It's a gradient vector field because this vector field is the gradient function or the gradient of some function little f. And in this case, we can find that particular f just by observation. But one can naturally ask, okay, well, what if I didn't know this was 1/2 x squared minus 1/2 y squared? Maybe you're not good at guessing these particular things. So let's ask this more general question. So given the gradients of little f, and let's call that, for example, capital F, can we always find a function f that satisfies? Take a moment and maybe pause or think about this. Will this be yes or will this be no? I'll just go ahead and tell you the answer is no. You cannot always find a little function f whose gradient is equal to the vector field that is given to you. Right? So let's bring back or look at a particular vector field. So let's assume that f, i.e. the gradient of f, but we don't know what little f is equal to minus yx. And I leave to you to verify that the graph associated to this particular vector field is going to be pointing that direction there, that direction there, this direction there, this direction there. And once you extrapolate these and create vector flow lines, what you'll actually get is a bunch of concentric circles. Right? It's almost like water rotating or curling around the origin. Right? But, you know, that's not very interesting maybe to you, but the natural question that we're trying to answer is, who is f? Right? So what we're going to do is we're going to try and reconstruct this little function f that satisfies. So let's suppose that there exists an f such that the gradient of f is equal to minus y and x. So this means that the partial derivative of f with respect to x has to be equal to minus y, and the partial derivative of f with respect to y has to be equal to x. So what we pretty much are left with is the system of partial differential equations. Right? So let's start off with the very first equation that we have here. So if the partial derivative of f with respect to x is minus y, then that means that f xy will be equal to minus xy plus a constant. But remember, if that function has only y in it, it does partially differentiate off to 0 with respect to x. So this is going to be a constant function with respect to y only. And it could have some numbers in it, sure. Now let's take the partial derivative of this function with respect to y. So that's going to be equal to minus x plus the derivative of g with respect to y. And keep in mind, this has to be equal to this particular function. This has to be equal to little x. So let's see if there does exist a function g that clearly defines f, because if we can find g, then we have our function f that satisfies our gradient equation. So let's look at this equation here and see what we have. So we have that g prime of y must be equal to 2x. But keep in mind, this is a function of y, and this is a function of x only. And this gives us a contradiction to our assumption that such an f does exist. Right? So that means there does not exist a function f such that the gradient of f is equal to minus y x. Right? So that means this circular flow that we see is not a gradient vector field. All right? So this then allows us or motivates the existence of the next definition. So a vector field, let's call it f, is said to be conservative if there exists some function, let's call it little f, such that the gradient of little f is equal to the vector field. And this function f is called a potential function of the vector field, capital F. Right? So not all vector fields have potential functions. We've just done an example of that. And let's actually give an example of one that does and one that does not. All right, so example 1. So if capital F x y is equal to x minus y, then we know that the gradients of 1/2 x squared minus 1/2 y squared will be equal to fxy. And since this does satisfy that, that means this is a potential, because we can technically put a constant there, f. So that means this potential function exists. So this means this potential function exists, which means that f xy equals x minus y is what we refer to as a conservative vector field. Now, the meaning of what we mean by conservative won't really make sense, at least to me, unless we start looking at the physics applications of this, which we will get into in the future. But for now, we'll just take it as a definition. And if we have fxy to be equal to minus yx, which seems very similar or close to the first vector field, but we've already verified that there does not exist some function, little f, that satisfies this particular equation, right? So this function f doesn't exist. So since that function f does not exist, and we've already shown how to prove that, that means no potential function exist, which means that the vector field fxy is equal to minus yx is not conservative. So if you can find a potential function, it's conservative, and if you can't find one, or moreover, if you can prove that it doesn't have one, that means that vector field is not conservative. So let's consider an arbitrary two-dimensional vector field f, whose first component is u and its second component is v, both functions of x and y. Then we say that the curl of this vector field is equal to the number, the partial derivative of g with respect to x, minus the partial derivative of f with respect to y. Now, where does this formula come from, and why do we want to define curl of this function to be this way? That'll become clear a little bit later on, so we'll just take this as definition for the time being. So what is the curl of a vector field? Well, at a particular point, it's a number, but the curl of a vector field is technically a function of x and y. And then you can plug in a point, x and y, into that function, and you can find the curl of the vector field at that point. So if we look at our prototypes of vector fields, in particular fxy is equal to x minus y, and our second field, gxy, is equal to minus yx, then what will be the curl of these vector fields with this definition? And since you have this definition and these vector fields, I highly suggest pausing the video and try these out on your own. So the curl of f, in this particular case, is going to be equal to the partial derivative of g with respect to x, so that's going to be equal to minus y, minus the partial derivative of f, which is going to be x with respect to y. Right, so that's going to be equal to the partial derivative of that with respect to that. Now notice that minus y doesn't have x in it, and x doesn't have y in it. So that's going to be equal to 0 minus 0, which is equal to 0. And if we look at the curl of g, that's going to be, again, the partial derivative with respect to x of the second term, which is going to be equal to x, minus the partial derivative with respect to y of the first term, which is going to be equal to minus y. So that's going to be equal to what? So that's going to be equal to 1 minus negative 1, which is going to be 1 plus 1, which is going to be 2. Right? Again, let's go back to the graphs of these vector fields, just in case you have forgotten. So what did x minus y look like? So that was this saddle point looking vector field, and g had that circular look to it. Right? So when you think of the word curl, what do you think of? Probably you think of wrapping your fingers around in a cusp or a circle or like the letter C, right? You know, you curl your fingers from a straight to a C. So what we pretty much see here is that the curl being equal to 2 gives us this rotational symmetry look to the vector field. Whereas if we take this vector field f and rotate it, it doesn't really have much rotational symmetry. So that's pretty much what the 0 is going to represent for us. So if we create a little summary chart of what we have here, so we have our vector field. Let's actually do it in 2 separate colors. Let's do that field here, and then this field here. So we have our circular field here, and then we have our field here. So let's draw our flow lines in a different color. Let's do those arrows here, and then let's do those arrows here. And let's also label our functions. So let's do fxy equals minus yx, and then fxy is equal to x minus y. So what things do we know about these particular vector fields? Let's summarize. So obviously this has rotational symmetry just by looking at its graph. Also, the curl of f is not equal to 0. We also know that it doesn't have potential functions. That is, there doesn't exist a function f such that the gradient of f is equal to this, which means it's not a gradient vector field. And also, due to that, it's non-conservative. Whereas for this second vector field, what we have has no rotational symmetry. That is, if you slightly rotate this coordinate plane by, say, 1 degree, it will not line up exactly onto what it used to be. Whereas if you rotate a circle, it's still a circle that overlies on top of it. Also, the curl of f will be equal to 0 for that one. Also, potential functions exist. And due to that, it is a conservative vector field. Now, these are just observational things. So 1, 2, 3, and 4. 1, 2, 3, and 4 for these particular vector fields. But what you're actually going to see as you play more and more in the realm of vector calculus, these properties will most of the time, if not always, stay like this. That is, if you have a conservative vector field, then you're always going to have a curl of 0. You're always going to have potential functions, and the graph will not have rotational symmetry at or near those points. Whereas if you have a non-conservative vector field, the curl will be non-zero, either positive or negative, no potential functions will exist, and it will have some sort of rotational symmetry. A couple little points that I want to mention about the curl when it's not equal to 0. When the curl is positive versus the curl is negative, and this goes back to, why do we define it this way versus another way, say. Usually we like to think of angles in a counterclockwise fashion. So that's why in this particular example, for this particular vector field, the curl was equal to 2, which is a positive number. So this is going to agree with our counterclockwise convention for rotation. And if you have a curl that is negative, then by definition what you're going to see is a clockwise rotation. All right, so those are just some observational things that we'll actually prove rigorously later on once we have a little bit more theorems. But for now, we'll just take them as observations that will hopefully extend later on. So let's actually go through another vector field, one that we haven't explored. Let's consider fxy to be equal to 3x squared y plus y cubed, and then x cubed plus 3xy squared. Right? So what can you say about this particular vector field in terms of the 4 properties that we stated above? For example, is it conservative? Does it have potential functions? Does it have rotational symmetry? What is the curl of this particular vector field? So take a moment and pause this video and see if you can find out any of the conclusions. Does it, follow more of the behavior of the saddle surface, or does it follow more of the behavior of that rotational circular surface that we mentioned before? All right, so let's get right into it. So let's take, for example, f to be equal to this, and let's call that little function g. So if I take the partial derivative of f with respect to x, that's going to be equal to what? So that's going to be equal to, so the partial derivative of f with respect to x, let's assume that this is the derivative of some function, little f. All right, so let's assume that this is equal to the gradient of f. So if this is equal to the gradient of f, that means this is going to be equal to fx, and this is going to be equal to fy. I think that's better. All right, so that means fx xy will be equal to 3x squared y plus y cubed. So let's see if we can build potential functions out of it. So that means fxy will be equal to x cubed y plus xy cubed plus some function of y. And then we can take the partial derivative of that with respect to y, and that's going to be equal to x cubed plus 3xy squared plus the derivative of g. Again, if this is a vector field that has potential functions, then this needs to be equal to this particular expression, in particular x cubed plus 3xy squared. Now, can we find some function g that is a function of y only? Hopefully, as long as what we have here with x cancels completely. And notice that they are mirror images, so what we have here is that g prime of y will be equal to 0, forcing g of y to be equal to just a constant, which is technically speaking a function of y only, or moreover, it doesn't have x in it. So potential functions do exist. Right? So potential functions exist. In particular, they look like fxy is equal to x cubed y plus xy cubed plus c. Right? So by definition, since potential functions exist, that means our vector field is conservative. It is conservative. So if our observations were true about conservative vector fields, then that means the curl of f is equal to 0. Now, we haven't proven that this is always the case, so let's actually work out a computational proof for this. So what is going to be the curl? So the curl of f is going to be equal to the partial derivative with respect to x of x cubed plus 3xy squared minus the partial derivative with respect to y of the first component, 3x squared y plus y cubed. So what's that going to be? So 3x squared minus 3y squared plus, and then minus, with respect to y, that's going to be 3x squared plus 3y squared. And then we look at these particular expressions. Are they equal to each other? So we have 3y squared minus 3y squared and 3x squared minus 3x squared. So both of them cancel off completely. So that is equal to 0. So the curl being equal to 0 still holds for this particular vector field that is conservative. So that's actually pretty nice. And what about the next observation here? So we have the first thing. So the first observation was that potential functions exist. 2, by definition, it is conservative. 3, the curl, is equal to 0. So what about the graph? So if the curl is equal to 0, that means it should not have rotational symmetry. So obviously you cannot verify this unless you actually look at the graph of the vector field. But we already know how to graph vector fields. But once you have the time, I highly suggest verifying this on your own. So what we're going to have is we're going to have these lines here. And we're going to have these lines here. Almost like slant asymptotes, I guess you could say. And what you're going to have here is this type of behavior, this type of behavior, this type of behavior, and that type of behavior, where we have that particular style, right? So obviously this is just a saddle surface rotated, which obviously does not have rotational symmetry, right? Because technically speaking, if it did, then that means the original one would also have rotational symmetry as well, since this is just a rotated version of this. Right. So we're going to get more into curl a little bit later, in particular the three-dimensional version of curl, which has a slightly different definition in terms of cross products. But these are some of the basics that you definitely need to know when you're working with vector fields, in particular conservative vector fields, potential functions, and the existence of curl being or not being equal to 0. Hope you enjoyed this video, and I'll see you in the next one. Take care.
Yeah.